This lecture is to provide an initial overview of the Haskell programming language. And in the first part of this course, of this overall course, we'll very much focus on Haskell as a programming language and even Haskell as a general purpose programming language. We'll pick examples from the field of cryptocurrencies where possible, but nevertheless, the goal is to just learn Haskell in a way that you can any program in Haskell. And the reason is partially because Haskell is the main implementation language for Cardano and is deemed important by IOHK, but also for the second part of the course where we'll look at Plutus and Marlowe. Haskell plays a big role in these as well. So Marlowe is essentially a Haskell domain-specific language turned into a standalone language. And Plutus is very much based on Haskell. And while you can certainly learn these smart contract languages on their own, you'll be much more competitive and better developer and more knowledgeable if you have firm understanding of Haskell first. That's why we do it in this order. Okay, so the goals of this initial overview lecture are to just look at what is Haskell and look at a few examples and to introduce you in particular to the big concepts of Haskell, all in one go in a way, but on a relatively high level. So Haskell is, I don't know exactly what your background is with respect to programming, but it is quite different from most other programming languages that are widely used and quite different in a lot of different aspects. So it's not just one new thing to learn about, but possibly quite many new concepts. And introducing you to these concepts one by one, the goal of this lecture is to essentially throw all these concepts at you at least once, but relatively superficially, so that you have heard about the terminology and when sort of big lines, what's coming. And then in the next lectures, we're going to deal with everything again in much more detail. Right? So this also means that you shouldn't feel like you have to understand everything completely just now. Hopefully you'll get a feeling for how the look and feel of Haskell is and make your first basic steps towards getting familiar with the language. Okay, all right. Let's first look at the historical perspective, perhaps, of Haskell. Haskell is not actually a very recent language. It is quite a number of years old by now. And it's been, the origins of Haskell go back to the late 1980s, and it has a very academic background originally. So it's really that at the time, there were a number of universities which were interested in functional programming, and they became interested in this new thing. At the time, it was a new thing. It was called lazy evaluation. And we'll look at what lazy evaluation is later on. But that was a hot topic in research at the time. In order to experiment with lazy evaluation, these universities developed their own systems. And there were a number of these systems, languages like lazy ML, Orwell, Gopher, and so on and so forth. And essentially every university that was interested in this adopted their own little thing. They took a language that already existed, made a couple of modifications, and started playing with it. And that was not very nice because everybody had their own dialect, and like university researchers in principle agreed that it would be much nicer to agree on some common language that would then also allow to write like more real programs rather than just toy examples. So they actually formed a committee and tried to standardize a language. And in many cases, that is a recipe for failure. But in the context of Haskell, it actually succeeded. And I think it's rather impressive that it succeeded and succeeded rather well. So this initial language committee did really great work and had a lot of fruitful discussions. And they released the first version of the Haskell report in 1990. At that time, also implementation work began, and there were a couple of efforts to create Haskell implementations. And all in all, there was a very active phase of language development in the 1990s, where several iterations of the Haskell report were released, and also the implementations were beginning to take shape. Up to roughly 1998, 1999, when Haskell 98 was released as a standard, and that was more or less the end point of this initial process that was considered a reasonably stable point. And then if you look at the standards, the Haskell language standards written in the report, really not much happened since then. So there was a minor revision of the standard in 2010, and there have been a number of efforts, but not very successful, unfortunately, to try to create yet another revision of the Haskell standard. But nothing really major has happened as far as the core language is concerned. But then, at the same time, there has been one major implementation that has been dominating. So there have been other Haskell implementations over the year, but they have been playing a much more minor role, and the dominating implementation is the Glasgow Haskell compiler. And one of the reasons it's so successful is that it's always been pursuing a relatively open development model, encouraging others to bring in their own contributions. And a lot of people have been trying to experiment with Haskell variations or with language extensions by getting them into the Glasgow Haskell compiler and making them available as language extensions. And in fact, there has been a huge amount of language development still in Haskell, and there are now literally 100 or even more different language extensions available. But the standardization effort has stalled. For one thing, that means that the core language is really considered rock solid and stable, and that's good. And most of what we're going to learn about initially is all standard Haskell in that core. Also, there are thriving developments around the edges, and towards the later weeks in the course, we'll probably consider quite a few of the language extensions as well, at least of the most widely used ones. So yeah, there's the landscape of Haskell and its history. Now, if we look more at the technical side and the Haskell features, first of all, Haskell is a functional and statically typed language. What that means, I think, hopefully we'll be able to make clear already during this lecture to quite some extent. It supports something that's called algebraic data types, of which we'll also see examples. Then it has this very powerful type system. In particular, it's powerful because it offers a very good form of type inference. So that means you don't necessarily have to specify the types of the things that you're writing. The system will try to infer them, to automatically derive the types from the code that you've written and make sure that everything is consistent and makes sense. And that is a very good compromise between having a powerful static type system and not putting too much of a burden on the programmer to always specify partially redundant information, because this type inference really tries to figure out a lot of stuff on its own, and also allows the system to help you by you being able to ask GHC, the Haskell system, what is the type of this? And then it'll tell you. And polymorphism, again, is a mechanism that allows you to avoid this trap that classic old-style statically typed languages have often run into, that type systems are mostly perceived as a hindrance because they are blocking valid uses of your code. But we'll see more about what that actually means. Then there is a feature in Haskell that's called type classes. So that sounds a little bit like object orientation, but really it isn't. So perhaps that is one of the pitfalls. But type classes are a little bit like interfaces in OO languages, but that's the closest correspondence. But it also provides a means of reusing stuff a lot of times. And then we come to the last 2 points, which are probably the ones that are what makes Haskell most unique. The first of them is explicit effects. Often this is slightly informally called that Haskell is a pure language. It essentially means that every program that is having side effects, things like doing input-output, doing network communication, computing random numbers, accessing the system time, doing concurrency, this sort of stuff. Every program that is doing side effects is specifically tagged in the type system, and you can distinguish by their types programs that perform side effects from programs that don't. And then the final point is lazy evaluation, which is the thing that originally sparked development of Haskell. That is an evaluation strategy that says that only things that you actually need are going to be evaluated. These days, I would say this is still a feature that makes Haskell rather unique, but it is perhaps not the most decisive one. I think explicit effects is really like, and the overall power of the type system. I think these are the things that make Haskell worth using, and lazy evaluation is a nice add-on perhaps, but it does have advantages and disadvantages both. We'll look at all these things in a bit more detail. So the goal of the rest of this lecture is to essentially fill all of these with a little bit more content than I've just given, and give you some examples of actual Haskell code. And then in the next few lectures, we're again going through essentially this list and filling all of these points with a lot more detail, so that you hopefully actually understand them fully once we cover them for the second time. Okay. Yeah, so as I said, functionally and statically typed languages, there are actually quite a few out there. They're all perhaps not extremely widely used, but functional statically typed languages include languages such as standard ML, OCaml, Scala, F#. So yeah, there are quite a few of these languages, and they all essentially have algebraic data types. Type inference and polymorphism is also, to some extent, a shared property between them. Type classes are relatively unique to Haskell, and explicit effects and lazy evaluation are really specific to Haskell. There are a handful of other languages, most of them are inspired by Haskell actually, that have these as well, but relatively few. Okay, so let's look at our first pieces of Haskell code. And let's start with this, probably the core of Haskell, and that is data types and functions that operate on these data types. And because this is Haskell and cryptocurrencies course, we are going to look at our first Haskell data type, and is going to be an extremely simplified version of a blockchain. Extremely simplified, you'll see in a moment. So let's talk about terminology, and then I'll explain in more detail. These are lines of Haskell code you see there. And there are data types here. So chain is a new data type that is defined in these 3 lines up here. And that is a definition of this data type chain, which is newly introduced. And int is a reference to another already existing data type of integers. And then data types are defined by specifying data constructors, and every data type can have one or multiple data constructors, and these are ways to create values of that data type. And our chain data type here has 2 data constructors. The first one is called Genesis block, and the second one is called block. And then constructors can have arguments, or sometimes these constructor arguments are also called fields. And the Genesis block constructor has no arguments, so it stands on its own. And this block data constructor has 2 arguments, and one is of type chain, and one is of type TXS, which is short for transactions. And then finally, TXS in this case, and this is where the huge amount of simplification takes place, is defined to be just an integer. So what we are describing here is something like a chain, but the chain contains nothing but plain integer values. And that is, of course, still very far away from an actual blockchain, where the blocks contain a lot of information, as we've already seen in the last lecture, like hashes and actual data about transactions and metadata, like when this block has been produced, transaction fees. So all this we don't consider right now. We simply assume that the chain is a sequence of blocks, each of which contain only an integer. And then the idea of this chain data type, which is recursive if you look at it, right? Data chain refers in this block constructor to chain again, is that you can build chain values by, you can build a trivial chain value by just saying Genesis block, and that is a chain that stands on its own and has no further data. But then if you already have a chain, you can apply this block constructor and extend it with a value of type TXS, which is just an integer. And you can create a longer chain that has an additional integer. And then by repeatedly applying this block constructor, you can build longer and longer chains. And here are some examples of this. So these are Haskell bindings. That is, the bindings are marked by the presence of an equals symbol, right? And so this is saying chain 1 equals block Genesis block 2. And as I said before, Genesis block stands on its own, so that is a trivial chain. And block is a constructor that takes two arguments, the first one being an already existing chain, of which Genesis block is an example, and the second one being an integer. So block Genesis block 2 is a valid chain with one block, if you like, or one proper block, and it contains one integer, which is this integer 2. Right? And the function application syntactically, as you can see here, so block is a data constructor, it doubles as a function, is just written using space. That is perhaps syntactically one of the most unusual things that beginners struggle with a lot. So if you want to apply a function to an argument, you just write the argument separated by space after the function. So this is block applied to two arguments, the first one being Genesis block and the second one being 2. And so let's again look at terminology. So the whole equations are called bindings. The things to the left of the equals are called left-hand sides. That is the thing that you're defining. That is an abbreviation, an identifier that you're defining to be something, right? A constant in this case. The things to the right-hand side of the equals are called right-hand sides. And the things that occur on the right-hand sides are called expressions, Haskell expressions. And expressions are essentially nested function applications and constants. And so all these sub-blocks that appear in the expressions are still expressions, right? 2 is an expression, block on its own is an expression, and so on and so forth. These are all sub-expressions. Let's look at the chain 2 and the chain 2 prime. So chain 2 is extending the chain 1 that we've just defined with another block that is containing the integer 4. So it actually denotes a chain that has 2 blocks, one being containing 2 and one containing 4. And so we can use things that we have defined using bindings in other expressions on the right-hand side. So we can use abstraction in this way. And whether we define chain 2 in this way, or whether we define it in this way by inlining the definition of chain 1, as we've done here, that really doesn't make a difference. That it's essentially the same chain value. And chain 2 prime, this is a common way in Haskell to denote a variant of something. So prime, this is just a valid character that can occur in identifier names. And very often, if you define multiple variants of something, you're calling them FF prime, F double prime, or something. That's just a convention. Okay. It doesn't have any special meaning. This is not an operation of some sort. It's just part of the name. So let's look at our first function now. Chain length is a Haskell function that operates on our chain data type and computes the number of blocks, not counting the Genesis block in this case. And such a function definition is also done by means of equations, but you can have multiple equations that define a single function. And you can optionally have a type signature, what's called a type signature. And type signatures are optional because Haskell has type inference. So if you don't write this type signature, which I've just shown here, then the compiler will still accept it and will infer the type for you. But even though you have that option and you can use it during development in order to let yourself be guided to some extent, types are providing a lot of guidance, and they also serve as a good documentation vehicle. It is very good style and absolutely encouraged to write down these optional type signatures for our functions so that we can immediately see what they are doing in rough terms. So chain length is of type, this double colon symbol here in Haskell is read is of type, a function from chain to, this arrow is the function arrow, so chain to integer. So it takes a chain as an argument, it produces an integer as an output. That is how to read this type signature. Again, so in terms of what everything's called, so this is, as I said already, an optional type signature. Then a function definition consists of one or more equations. Sometimes this is also called cases. And again, we have left-hand sides, but now on the left-hand sides, we have not just the name of the function being defined as before when we had our constant bindings, but we also have something that is called patterns. The patterns are saying, like, depending on what this chain is, what are we going to do with it? Patterns play a big role. We're going to look at them in more detail. And then on the right-hand side, we again have expressions. And one thing that is very common to a lot of Haskell code is recursion. So recursion is ubiquitous, happens everywhere. And what we see here is that we have a recursive call to chain length in the block case of this chain length function. So now let's briefly look at what this chain length function means. So you can read this as a case distinction. So we have seen that the chain data type has two data constructors. So there are two ways to form chains. If you turn this around and you get an unknown chain given to you, that also means that there are just two ways how it could have been constructed. And you can ask, whenever you get something, like, which of its data constructors does it belong to? Which shape does it have? So if the chain given to us is a genesis block, then we say the length of that chain is 0. If the chain given to us has been constructed using block, then we have access to the two arguments of the block constructor. The first argument being the chain that has been extended, that is the smaller chain that has been extended. The second one, written using underscore here, being the integer that is stored in the chain. In this case, we want to give a name to the chain being extended, and we don't need to use the integer. In order to compute the chain length, we don't need to know what has been stored within the blocks. How do we compute the length of such a chain? We recursively compute the length of the chain that has been extended and then add 1. Again, syntactically, function application binds very strongly. So that means chain length applied to C. That is the function application that we're computing here. And then to the result of that, we're adding 1. So plus 1 is binding more weakly than the function application chain length to C. No parentheses are necessary here, even though you could use them in order to highlight the grouping. Let's try if we can get a little bit of interactivity into this and whether you're all still following to some extent. I would like to know, just given what I've said so far, if I would replace this 1 here, yeah, the 1 that is listed here, if I would replace that with a 2, then what would chain length do? How would the behavior of chain length change? Yeah, for every block would be counted as 2 rather than 1, so we would end up with double the length of the chain, exactly. What would happen if I would replace this 1 with 0 instead? Yeah, then the output would be always 0, exactly. And then I would count every block as 0, and every chain that I would feed it would add up a number of zeros. The end result would still be 0. And then finally, perhaps the hardest of these questions is what if I would, or perhaps not, depending on how familiar you are with this, if I would drop this whole chain length C recursive call here, and I would just write the second case to be equals 1, then how would this function behave? It would then return 0 for the genesis block and 1, always 1, for any chain that is not the genesis block, right? It would not traverse the entire chain anymore, but if there is at least one proper block, it would just return 1 if you drop the whole recursive call here. Okay. If you want to play with this, you can load up programs in GHCI. Let me show this briefly in actual code. So there are probably 3 tools that you are going to interact with next to an editor sooner or later. There is GHC, which is the actual compiler, which you're in the beginning rarely directly interact with. So that is the Glasgow Haskell compiler. Then there is an interactive version of this, which is part of the same installation. So if you have GHC, you always also have GHCI. And then there is Cabal, which is a packaging and tools tool, which we'll sometimes be using as well, in particular if it comes to larger programs. So GHCI can be invoked just on its own. and it will greet you with a sort of GHCI version 8.10.1 and so on, and it will tell you that you can type this for help, and it will give you a prompt that is prelude. I'll explain later what that means. And at this point, you can now type Haskell expressions and also, to a certain extent, Haskell declarations such as bindings. And I can, for example, type something like 2 + 2 and I get 4. I can also type something like 2 is 2 equal to 2 and I get true. I can apply something like a function called not to a Boolean called true and I get false. And there are quite a few things that you can do. And additionally, you can also issue commands to GHCI. GHCI commands start always with a colon. Probably the most important command initially is to see how you get out of GHCI again, and that is called :q for quit. And then you can leave GHCI again. Okay. So now, if I type something like chain length of chain 1, then it'll complain because these are definitions that I've made on my slides, but they're not predefined in Haskell or anything. So chain 1 or chain length, these are functions that I would have to define in a source file on my own. But if you have a Haskell source file, you can load these source files into GHCI. And how to do that, I will explain a little bit later. But I have done this here. This is an environment where I'm also in GHCI and I can still type this, but I have the definitions from the slides available. And here I can say something like chain 1, and I can get this chain printed back at me. So it says chain 1 is this chain that extends the Genesis block with 2, and chain 2 was a chain that extends this chain 1 once more with a block containing 4. And then I can actually try the function that I have defined, chain length, and I can call it on chain 1. Again, function application is just a space, and chain 1 contains 1 occurrence of block and then immediately the Genesis block, so it should give me 1. And chain 2 is having 1 block more, so that gives me 2. I can try to extend the chain a little bit further. So I say if I extend chain 2 with another block containing 33, I'll get a chain of length 3. Okay. And ultimately, if I call chain length just on the Genesis block. Okay. So that is how you can use GHCI. This is still in a trivial setting, but it is quite valuable to gain experience with Haskell, in particular initially. So you are really encouraged to spend a lot of time initially just trying things out in GHCI. And obviously you'll make mistakes, you'll get error messages that you don't fully understand initially because we haven't covered all these things. But don't let that discourage you. That is part of the experience, okay? But we'll cover things eventually, and we have to start somewhere. So this GHCI tool is very useful to interactively play with Haskell programs. Yeah, these are similar examples. You can also build expressions in GHCI, such as I want to compute the chain length of chain 1 and then add 1 to it, right? That will give you 2. Or I want to test whether the chain length of chain 1 is equal to the chain length of chain 2, because this one is 1 and this one is 2. This will give you false as a result. If you look at how Haskell evaluates stuff, then the main way to think about evaluation in Haskell programs or how Haskell programs run is not like in an imperative language where you typically say first this thing happens and then that thing happens, but it is by looking at an expression such as one that you could type into GHCI and transforming it step by step according to the equations defined in the Haskell program until you no longer transform it and have a final value. And I'll show this as an example here. So chain length of chain 2, if you type this in GHCI, then what GHCI will do is it'll look at how chain 2 is defined. And chain 2 was defined to be block chain 1, 4, right? So this is just a rewrite according to the equation that defines chain 2, okay? And now, if you look at how chain length was defined, it was defined using 2 equations, one for the Genesis block and one for block. And because this is not the Genesis block, the first equation, the one for Genesis block, does not apply here, but the second one applies. And that's why these patterns are called patterns and why pattern matching is called pattern matching. So if you have such a call, GHC or Haskell will try to match your call against the patterns that are the left-hand sides of the function definition and see which of the cases apply. And in this case, the case for block applies, and then the left-hand side is replaced with the right-hand side. And that leads us to say, to the expression chain length of chain 1 plus 1, right? Because if you remember how if we go back, how the second case of chain length looked like, it's that if we have a block where the first component is C and the second component is an underscore, then the right-hand side is chain length of C plus 1, okay? So C in our case is chain 1, and we don't care about what the integer is, so we get chain length of chain 1 plus 1, okay? At this point, GHC will actually try to evaluate the plus because it's the outermost function call, but in order to evaluate an addition, it has to know both the numbers, the one on the left and on the right, because the number on the left is not known. It will try to evaluate chain length. In order to evaluate chain length, it has to know, again, which of the patterns match. In order to know which of the patterns match, it has to look at chain 1. So the equation for chain 1 was that it was defined to be block Genesis block 2. So we replaced this line by this one. And now again, we can look at the definition of chain length. Again, the second case applies, and we can rewrite this to chain length of Genesis block plus 1. And now the same argument applies. We cannot evaluate this outer plus because we don't know what the left number is. We cannot evaluate this plus because we don't know what the left number is. But we can evaluate the chain length call to Genesis block. And that is now the first equation of the definition of chain length, where we said chain length of Genesis block is 0. And then we have 0 plus 1, and then we can perform additions, and then we end up with 2. So this step-by-step evaluation process is at the heart of what Haskell is doing. Now, in practice, if you compile a Haskell program, there is an efficient compiler that produces native code, and it does all sorts of optimizations, and it doesn't actually perform this symbolic reduction step by step. It does the same thing in a much more efficient way. But if you think about evaluation, and if you're interested in reasoning about what will be the result of evaluating an expression, then this is the right mental model to use. And one of the good things of Haskell is that this scales up to even large examples. Of course, expressions will be far more complicated, and you may have to write endless amounts of code, but locally you can still perform these equational rewrites and reason about certain programs being equivalent to certain other programs. And this is why this style is important, and this style of reasoning has a name, and it's called equational reasoning, and it's at the heart of Haskell evaluation. Let's go on and let's talk about types, because we've now been looking at data types and functions, and we've seen our first examples of data types and bindings and functions. And now types play a big role. So in order to talk about types a bit more, we'll look at one more example of a function. I just practice this a bit more. And actually, this is a function that has 2 arguments. It's called hasBlock, and it tests whether a given chain, has a block with a particular value. If you, for example, ask if our chain 2 contains 4 as an integer somewhere among the blocks, then the answer would be yes. If you ask if our chain 2 example value contains 5, then the answer would be no, because we had just the blocks 2 and 4 in there. So this hasBlock function is supposed to take an integer x and a chain, and it's supposed to test whether that integer is occurring as the value stored in one of the blocks. And how is this done? This is done again by giving 2 equations, by pattern matching on the shape of the chains, having one case for the Genesis block and one case for proper blocks. If we ask what is hasBlock x of the Genesis block, the Genesis block contains no elements, right? It stands on its own. So if we ask whether x is contained in it, the answer is always no, false. If we ask whether x is contained in a chain of the shape block CT, then we have two options. Perhaps if the x is equal to this integer t, right? This was our integer here in that block. And if it is, then clearly x is an element of that chain. But if that's not the case, and this is a logical OR operator in Haskell, double bar, then we can recursively look in the rest of the chain. So then we can ask whether x is an element of C, of the rest of the chain. And again, this is recursive, but we'll test, is x the sort of the topmost element of the chain, the one that has last been added, or has it been added before or before? And if it's nowhere, then we'll sooner or later hit the genesis block, and then we'll say no. Okay. Now this is, again, a function definition with two equations that we can just write like this, but it would be nice to write a type signature. If you look at what is the inferred type of Has block in GHCI, and that introduces a new GHCI colon T, which is really nice to know. It asks GHC, what is the inferred type of a Haskell expression? Then GHCI will print back this. Has block is of type TXS, arrow, chain, arrow, bool. And we'll have to talk about what that means. Let me just briefly show colon T again. So even for the things that we have so far, I can ask, for example, what is the type of the inferred type of chain 1? And it'll just say this is a chain, right? And if I ask inferred type of chain length, it'll say it's a function that goes from chain to integer. I can put an expression here as well, I like a compound expression. If I ask what is the inferred type of chain length applied to chain 1, then I've supplied the chain, then the result is an integer. And again, this double colon always reads is of type. So you can read the answer here as chain length applied to chain 1 is of type int. Right? It is an integer. And what is the inferred type of Has block? That's transactions to chain to bool. I think, okay, this is a deviation from the slides, unfortunately. Here it's called transactions. On the slides it's TXS to save horizontal space, but that is just because it's defined differently. The perhaps confusing thing is this double occurrence of the arrow, right? If we look at the definition of Has block again, it looks like it's just defined as a function of two arguments. They're both separated by space. And also, if you look at the call of Has block in GHCI, if we apply Has block to 4 and chain 1, then we get false because chain 1 contained only a single block, namely 2. But if we ask Has block of 4 and of chain 2, then we get true. So it looks like a function of two arguments, but the type is this strange repeated occurrence of the function arrow. And this is what's called currying. That's the technical term for it. And the idea is that one way to look at Has block is as a function that takes one argument that is an integer, so a TXS value, right? And if you supply it with the argument, then what it gives back to you is another function, right? It's not immediately a plain result, but the result of supplying the first argument is another function, and that function that is remaining is expecting a second argument, and this is of type chain. So if you apply Has block to just one argument 4, then and you ask what is the type of that, then you'll be left with a function that still expects one argument, chain, arrow, bool. And then if you apply Has block 4 to another argument, which is of type chain, then you'll be left with the final result bool. If you see these repeated function arrows, they always nest to the right, and they basically, you informally still say it's a function of 2 arguments, right? Or a function of 3 arguments if you have 3 nested arrows. What it means in practice is you can supply arguments one by one, and whenever you supply one argument, you are left with a function that expects one less argument. The function application syntax is implicitly parenthesized to the left, so you can have these parentheses, you can also drop them. The function arrows are implicitly parenthesized to the right, so you can have these parentheses or you can drop them. But repeatedly applying these arguments supplies like these required arguments to the functions one by one. And so you can model arbitrary functions with 10 arguments or so as a nested function type that always uses just functions that have a single argument, but then deliver another function. So there aren't really built-in function types of 2 or 3 or 4 arguments. There is just this one function type that takes one argument to one result. Because a function can return a function as a result, you can use this to simulate functions with multiple arguments. And this fits nicely with the syntax, but it is also useful in practice because every once in a while we'll see examples where these partially applied functions, where you supply just a few of the arguments to a function, are actually useful on their own. And we'll see examples of this. Okay. If you look around and ask GHC for the types of all sorts of predefined stuff, you'll see that curried functions are everywhere, right? Whenever you have functions with multiple arguments, they are written in curried style. And we have seen these operators, we've seen logical OR already. And an operator in Haskell is just a function, and you can, in fact, use a symbolic operator as a standalone prefix entity or just as a standalone entity by surrounding it in parentheses. So symbolic names are just special names you can give to functions. And if you look at what the type of this logical OR is, it's curried bool to bool to bool. So it's an operator that takes 2 booleans and ultimately produces a boolean again. Similarly, logical AND is bool to bool. And if you ask what is the type of the block constructor, the data constructor for the chain type, it is also a curried function because it had 2 arguments. A block expects a chain to be extended and a value of type transactions, which was just a synonym for int, and then it produces another chain. Okay, so you really see a lot of these curried types. And as I just hinted at, operators in Haskell are just identifiers. They're just specific symbolic identifiers. You can define your own symbolic identifiers. There is no fixed set of operators. So you can choose what syntax you want. There is a lot of flexibility here. So if you have a symbolic identifier, vertical bar, then by default it is written in fix. So you write true or false with the operator in the middle. But you can enclose the operator in parentheses and then write a prefix or apply to true and false. That means the same thing. Similarly, if you have a alphanumeric identifier, which is the standard form we've seen, like block, then by default it is written prefix. And if you apply block to its 2 arguments, you write block space chain 1 space 4. But you can enclose it in back quotes and use it infix. So you can always shift around between infix use and prefix use. Really, whether you name something symbolically or alphanumerically is just a choice. In practice, using symbolic names that are not established in a particular community or field are a good recipe for making your code unreadable. And so Haskell sometimes has a reputation for doing that and overusing this feature. So be careful with defining your own operators without good need. I mean, use that with care, but it's good to know about this. Okay. Because there is no built-in list of operators, there are just predefined ones, and libraries can define their own, and you can define their own. There is another really useful command that is good to know about in GHCI, that is :I for info. And :I gives you information about where a particular identifier is defined, and sometimes, depending on what it is, it gives you additional information about that identifier. So you can, for example, ask GHCI, where is this OR operator defined? And it will tell you again, OR is of type bool to bool to bool. It'll tell you it is originally defined in a module called GHC classes. Actually, I'm not sure whether that is still true. That may be outdated. Let's just make sure. So it is still true. And it will tell you this little line here, which is the useful one for operators. It'll tell you that the OR operator is right associative. So if you have multiple occurrences of OR next to each other, then it will implicitly be parenthesized to the right. This is what this little r here means. And it has priority 2, and that is just a numeric scale that goes from 0 to 10. that all operators in Haskell are based on, and lower numbers mean it binds weaker than higher numbers. And we can, for example, look at that the logical AND operator has the priority 3, so AND binds more strongly than OR. You can just look that up using colon rather than having to look up one fixed table in a book. You can just ask GHCI. Similarly, as you would expect, plus, there's something about type classes here which we'll only learn about later, but plus is left associative and has priority 6, and times multiplication, as is usual, binds more strongly. So it is also left associative and has priority 7. Multiplication is binding more strongly than addition, which is the usual mathematical convention. Okay, let's go back to this. We can use this if we want to define a symbolic version of our block constructor. Right? This is just something that we can do. We can type signature, again, it's optional, but it's encouraged, of this bar greater than operator that we define ourselves, which is an infix version or a symbolic version of our block constructor. It has the same type as the block constructor. It extends a chain with a new transactions value. It delivers a new chain. We define it to be just equal to block. And we can give it our own infix declaration saying that it should be left associative and it should have priority 5. Okay, and then it's defined like this. We don't have to give such an infix declaration, then it defaults to something. I think it defaults to 9 and being not associative, but I would have to look this up again. But it's a good habit. If you define your own infix operators, provide an infix declaration for them to make it explicit, like what kind of priority they have and what kind of associativity they have. And then if we have this defined, we could alternatively, again, define the same chain that we've already defined in 2 different ways, chain 2 and chain 2 prime. We can define in yet another way by saying we want to extend the genesis block with 2 and then 4. That makes it much more compact. So we don't need to use these parentheses because we said the operator is left associative and we don't have the word block occurring in there anymore. So that abbreviates it quite a bit.
What's the difference between infix L and infix R?
So that means that the operator is left associative or right associative. So this plays a role. Let me give you an example. This plays a role if we write something like 5 minus 2 minus 3. So if you have multiple repeated occurrences of an operator like this, right, then how is this interpreted? Is this interpreted as 5 minus 2 first and then minus 2, which would result in 3 minus 2 being 1, right? Or is this interpreted as 5 minus and then 2 minus 2? In this case, it would be 2 minus 2 is 0 and 5 minus 0 is 5. So it matters for the result for some operators that are not associative. That's the property of the operator is called. So if something's defined infix L, then the first interpretation is chosen, like the parentheses are implicitly nested towards the left, L for left. And if an operator is defined as infix R, then the second interpretation is chosen. And so the parentheses are implicitly nested to the right. Now for minus, it is left associative, so you get 1 as a result, and you can see that by asking what is the info for minus, and you'll see the little L standing here.
I think you also have infix without L or R if error if you do this, right?
Yeah, so if you remove, if you just write infix and give it a priority, but if you then have repeated occurrences of the same operator like this, you'll just get an error. It'll say that it cannot resolve this. I can actually try this. Let me define my own version of minus, a fancy minus. Let me see. For example, this. All on one line here in GHCI. This is a little bit awkward. Normally, you don't use GHCI to define a lot of your own code, and if you do, you have to slightly strangely. So semicolons are usually not used in Haskell. You will write things on subsequent lines. But I define this operator to just be the same as minus, but I'll give a different declaration for it. I'll just say infix without a letter, and then perhaps also 6. and then minus. Now, if I do 5 minus bang 2, I'll get an error message that will say, yeah, because you haven't specified left or right, and there is a situation where this matters, you'll just get an error message. That is a third option that you can get. And if we would define the same thing to be right associative, then we would get this unusual result of this expression being 5, because then now 2 minus 2 would be evaluated first, and that would result in 0, and then 5 minus 0 is 5. Okay,